All right. I wanted to make a video to help you with graphing piecewise functions for homework too. I didn't get a chance to get to these in class, so I wanted to make sure that you had a resource to help you with this. So a piecewise function is a function that looks like this down here, this f of x. And basically a piecewise function is a function that has um, pieces of different functions kind of all put together in one giant function. I like to call these guys Frankenstein functions because we grab different pieces from different functions and we sew them all together into a giant monster function. So that's what a piecewise function is. And there's a few different things that we can do with piecewise functions. Specifically here, we're going to be graphing this. So I want to get a visual picture for what this looks like. So in order to do this, to graph a piecewise function, the first thing that I want you to do is graph each function on a separate graph. Separate graph. Okay, so what I mean by each function, down here in f of x, we would graph y equals 7 on one graph, y equals the square root of x on a second graph, and y equals negative x plus 2 on a third graph. So we'll graph all three of those on separate graphs. The second thing that I want you to do is cut out the correct section of each graph. Now, to do this, the cutting out part, we are going to use the indicated domain for that for each graph to kind of cut out the correct section. So this domain here, this for x less than or equal to negative 3, that will tell us what part of the graph y equals 7 we need. So first we'll identify each section of the graph and cut it out. And then the last thing that I want you to do is to graph all the cutout pieces, I'll say the cutout sections, together on a single graph. This is the part where we turn it into a Frankenstein function. We sew it all together on one graph and we have our giant monster graph. Okay, and then we're also going to be asked if that piecewise function is continuous or not. A function is continuous if the graph essentially is made of a single piece. And what I mean by that is there are no breaks, no holes, no jumps, nothing strange that would break this into two separate pieces. Basically, if you can draw the whole graph, if you can draw the whole graph without lifting your pencil, the graph is continuous. If you don't have to pick up your pencil, it's all a single piece, and it is, in fact, continuous. Okay, so let's try this process on this example number 1 here. So again, we've got 3 separate graphs. We've got y equals 7, y equals the absolute value of x, and y equals negative x plus 2. We are going to graph each of these on a separate graph. So I'm just going to make 3 different graphs here. And we're going to graph each of these on one graph. So this will be y equals 7. That's this first one. The second one will be y equals the absolute value of x. And this third one will be y equals negative x plus 2. Okay, so Alex's process is going to try to walk you through putting all of these things together on one single graph. Frankly, I think that's more confusing because it's doing too much. I like to graph a single function and then we'll identify each piece, and then we'll put it all together. All right, so y equals 7. What does this guy look like? Well, hopefully you're saying, hey, that's a horizontal line. Y equals, that is a horizontal line, and it's going to go through 1, 2, 3, 4, 5, 6, 7. It's going to go through y equals 7. So that's what y equals 7 looks like. All right, how about y equals the absolute value of x? Well, this is a back pocket function, so hopefully without thinking too much in your brain, you said, hey, this is a v. You drew a v. And then this last one, y equals negative x plus 2. What does this one look like? Hopefully you recognize we are in y equals mx plus b format. This is the equation of a line. This line has a y-intercept of 0, 2, and a slope of -1. So m equals -1 over 1. That's rise over run. So I'm going to rise -1, run 1, and here is my line. Okay, so that is, sorry, the perfectionist in me doesn't like this line, so I'm going to try again. I want it to be a little better through there. Okay, that makes me feel better. Okay, so now we have all three of our functions graphed. Now we need to to cut out the correct sections. So in order to cut out the correct section here, I'm going to start with y equals 7. Y equals 7 for x less than or equal to -3. So we only want the section of this graph where x is less than or equal to -3. Okay, so where is x less than or equal to -3? I'm going to come down here and say, well, x is -1, -2, -3 right here. So the point on my graph where x equals -3 is right here. And I'm going to close this point because there is an equal to sign here. I am going to include this point because x equals -3 is included in my graph. So this point is going to be closed. And then I want to include all the values for which x is less than or equal to 3. The places where the x values are less than or equal to 3 are over here to the left. So this is the section of the graph that I'm going to include from y equals 7. It's just from the point -3, 7 on over to the left. Okay, let's try the next one. Which section of the graph absolute value of x do we need? Well, we're going to look at our domain for this. And we only want the absolute value function for values of x that are between -3 and 2. So what part of this graph is between -3 and +2? All right, well, x equals -3 is over here at -1, -2. Here's -3. And +2 is over here at +1, +2. So I'm going to take these 2 points. I want the part of the graph that is between x equals -3 and x equals 2. So I want all of this part because that is all between -3 and +2. Now, do we need to include the points at -3 and 2? There's no equal signs on either of these inequalities, so that means we cannot include the endpoints themselves. So I'm going to have an open dot here. And I'm going to have an open dot here where x equals -3. But I'm going to include everything in between. All right, the last graph here is the -x here we go, negative x plus 2. And I only want the section of this graph where x is greater than or equal to 2. So I'm going to come over here and say, well, here is x equals 1 and 2. Because x can equal 2, I'm going to go to the point on my function where x equals 2, and I'm going to put a closed circle there. And I want the part of my function where x is greater than or equal to negative 2, which means I'm going to start at this point, and I'm going to take the part of my function that goes to the right, which means I'm going to take this part right here. And that is the part of the function that I'm going to take from here. So now I have all 3 sections of my graph, and now I just need to put all of these together on a single graph and create my Frankenstein function. So I'm sorry if this is a little messy. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. Okay. So now I'm just going to take all of these 3 pieces and I'm going to put them onto a single graph. So the part from y equals 7, I'm going to come here to the point negative 3, 7. So 1, 2, 3, up to 7. I'm going to put a closed circle here, and I'm going to go straight to the left. This is that red section from y equals 7. Next, I'm going to take this middle section from y equals the absolute value of x. This is the point negative 3. If I plug negative 3 into my function, the absolute value of negative 3 is positive 3. And this point here, if I plug x equals 2 into my function, y is the absolute value of 2, which is 2. So I'm going to plot these 2 points as open circles on my graph. So I'm going to go to negative 1, 2, 3, up 1, 2, 3, and put an open circle. I'll come down to the origin, and then I'll go from the origin up to the point 2, 2, where I'll have an open circle, and I'm going to come up here. And finally, from the graph of y equals negative x plus 2, this point here is going to be the point 2, 0. Again, you can plug x equals 2 into my function to make sure that that's the point 2, 0. So I'm going to put a closed circle at 2, 0. And I have a slope of negative 1. So I'm going to go down 1 over 1 and just connect those with a straight line. And this is my entire Frankenstein function for f of x. So I think it's easier to separate your graphs out, cut out the correct sections, and then put them all together. Alex wants you to kind of work with a single graph and kind of cut out the pieces that you need, and I find that to be more confusing. Worst case scenario, draw the whole function and then erase the parts you don't need. I find that to be a much easier process on your brain, and you'll make fewer mistakes. And just because this is a difficult concept, let's try number 2 here real quick. We have 2 pieces, 2 different functions to graph for this. So I'm going to draw 2 separate graphs. And so we've got y equals negative x minus 1. And over here we have y equals the square root of x plus 1. We're going to graph each of these functions separately. So let's start with y equals negative x minus 1. This is y equals mx plus b. I have a y-intercept of negative 1 and a slope of negative 1. So I'm going to come down 1 over 1. And here, I'm just going to draw this in. That's a terrible graph. Sorry, this is hard to get my angles right to get this straight line in here. Okay. There's y equals negative x minus 1. And we're going to graph y equals the square root of x plus 1. Okay, well, this is going to be a square root function. We know what that looks like. This +1 inside, we know from transformations, this is going to take the square root function and it's going to push it left 1 unit. So I'm going to take my normal square root function and I'm going to shove it to the left 1 unit. So instead of starting at the point 0, 0, I'm going to start at the point -1, 0. And I'm going to grab a couple more points and get those in. And again, I'm just taking y equals the square root of x and sliding it to the left one. That's where these points are coming from. You can always plug in a few different numbers if that helps. So this is what y equals the square root of x plus 1 looks like. Now we just have to say, okay, well, which points or which sections of each do I need? So -x minus 1, we want the section of that one where t is less than or equal to -1. And sorry, we've got some x's and some t's. This is a little strange. Let's call these all x's. Sorry about that, guys. So we want the parts where x is less than or equal to -1. Okay, the places where x is less than or equal to -1. X is -1 right here. And because it includes -1, there's an equal sign right here. I'm going to put a closed dot on my function at x equals -1. And I want the parts where x is less than or equal to -1. So I need to go to the left, and I'm going to include this section here. This is the part that I need. That's the section of this graph where x is less than or equal to -1. Okay, this next section, y equals the square root of x plus 1, I only want the section of that where x is greater than -1. Okay, x is greater than -1. I'm going to go where x equals -1, and I'm going to put an open circle on my function. It happens to be right here. So I'm going to put an open circle there, and I want the part of this function where x is greater than -1. So I'm going to go to the right. I want this section. That's the part of this where x is greater than -1. So now I've got my two sections. So to draw my overall graph of my Frankenstein function, I'm going to put both of these on the same graph. So I'll take my red section here and put it on my graph. I'm going to start at -1, 0. And this has a slope of -1. So I'm going to go up 1 over 1 because that keeps my slope intact. So I'm going to go up 1 over 1 to -2, 1. And then I'll connect these guys. And to take the section from here, I have an open circle at -1, 0. So if I put an open circle here, notice that the closed circle essentially fills in that open circle. So the fact that you have an open circle and a closed circle on the same dot is actually going to close that circle. It's going to keep it closed. The closed dot will kind of fill the hole in the open dot. And then we just need to fill in our square root function here. And there is my overall Frankenstein function for s of x. So that's what that's how to graph piecewise functions. I just want to go through and ask you if each of these is continuous or not. So back here in number 1, because this has 3 separate pieces, and if I start to draw this function, this part of the function up here, I need to lift my pencil off the paper and put it back down to come down here for this part. There's a break in that graph. This is not continuous. This has a few different pieces, and I have to lift my graph, or I have to lift my pencil to draw it. That's not continuous. Now notice this guy here, this is all one piece. It's all connected. I can start here and draw this section of the graph and then go ahead and just continue on. I don't have to lift my pencil to draw this graph. This is all one piece. It's connected. This is, in fact, continuous. All right, y'all, I hope that helps with graphing piecewise functions. Happy Alexing, and I will see you next time.